move on. Hello, my name is Mirko Goldmann. I'm a PhD student here at IFISC in my second year now, and I'm presenting a poster called Inferring untrained complex dynamics of delay system using a physics-informed reservoir. The work is done together with Claudio Mirasso, Ingo Fischer, and Miguel Soriano. In this work, we describe how we can inform a reservoir computer about the physics underlying the task, and having informed the reservoir in the testing phase, we will explore dynamics which were not part of the training. So in physics-informed reservoir computing, we use prior knowledge about the task, and then we bias the machine learning model using either training data, the reservoir's topology, or the loss function. After this, we drive the machine learning model with the data and learn only the output layer. Learning only the output layer in a reservoir computer is really simple because you only need to carry out a linear regression, which makes it really efficient. Together with those two ingredients, we reach high prediction accuracy, far-reaching inference, and data-efficient learning. In our example, we try to predict delay systems. Therefore, we introduce a delay into our network, as you can see here. We train with an chaotic attractor, and during the training, we learn to replicate the chaotic dynamics of the training data set. After having learned in the training, we go now to the testing. And in the testing, the network is decoupled from the external input, and it is driven by its own predictions. So it runs completely autonomously. When this autonomous running, we can further detune this delay of the network, and then the system predicts complex dynamics it has not seen in the training, but these dynamics are the original dynamics from the delay system it was trained for. So to be a bit more precise, we learn to make a class system with a really long delay, and the make a class system also has high nonlinearity. So this is usually used as a benchmark task for machine learning models. We physics inform our machine learning model by introducing also this delay term here. So the D is our delay. We learn for the one step ahead prediction by optimizing these W outweights. And after we find an optimal setting of the output weights, we feed back this y hat of n as the new input to the reservoir. In the figure here, you can see that the original trajectory in blue is almost identically reproduced by the reservoir, and only after 2000 steps it starts to visibly diverge. In general, there's of course a divergence between the original and the prediction due to the chaotic dynamics. But you can see here in this figure that the echo state network can reproduce the largest Lyapunov exponent of the chaotic attractor. As I promised more in the abstract, and I'll show you how we can go to the testing phase and predict out of the training data. Therefore, we train this example here at delay of 100. And then in the testing, decoupling the reservoir and setting the delay to 17 in the echo state network. What we observe is that now our reservoir really can predict the chaotic attractor of the Mackey class system with a delay of 17, while it has not learned how this attractor actually looks like. We further can go to different delay lengths like 39 or 200, and without changing the output layer or without any further training, we can really predict different delay lengths. This goes so far that we can entirely predict the bifurcation diagram of the delay system using only a single training example. In the lower part of the poster, I talk also about the limitations of this method. We found that the more complex the training data is, the better our machine learning model can learn from it, or the more it can learn from it, and the better the inference ability is. So we introduced here a comparison measures between the dynamics of the predicted and the original Mackey class system. And you can see if we learn at the Mackey class system of 100, we can predict all delays really good. If we learn at the Mackey class system of 17, we can predict the attractors with lower delays good, but going to larger delays, it starts to deviate. In general, we found that if you learn in the long delay limit, where local and delay dynamics decouple, which you can determine with this autocorrelation function here, if you learn there, you can predict even much longer delays. So for the Mackey class system with a delay of 100, train it with it, we can also predict the 10 times longer delay of 1000. To conclude the poster, and give a short outlook, I show you that we can train a physics-informed reservoir on data, and then in the testing phase, we can predict dynamical features which are not part of the training but correspond to the original system. This method enables us to build digital twins of real-world systems, which means given that you have a set of data and you know that in this data there's an underlying delay, you can build physics-informed reservoir and then can predict dynamics which are not accessible in the real world. And as an outlook, as we understand how the mechanism works and what are the requirements for the reservoir as well as for the training data, we believe that it is possible to build further extensions of this mechanism to other dynamical systems such as delayed coupled oscillators and spatial shuffle systems. With this, I'm done. I hope you enjoyed my poster, and if you have any questions, just tell me. Thanks.